Hi everybody, it's Mrs. Cassill. Here's the brief recap of what we covered today. Now this is a video, so remember you can pause it if I'm going too quickly to write things down. You can rewind it if you need to rewatch something. You can fast forward to just the part that you need. Use your video tools to make this easier for you. So we already set up our notebooks. So 5 terms today. Distance, the total ground covered by an object during its motion. So how far it is from where you are to Northurston High School. If you gave someone directions, they'd have to go by road, sidewalk, bike track, train track, they'd have to travel along the ground, which means they're going to go to the stop sign, then they're going to turn left, and they're going to go to the roundabout, then they're going to follow that curvy road on the other side. They're going to cover some distance. This is very different than displacement, which is the change in position of an object measured in a straight line. If instead you gave your friend directions from where you are to Northurston High School, and your friend thought, gosh, wouldn't it be easier to fly with my superpowers? And they traveled in a straight line through the air, they would have a very different path that they were taking. But think about it. The change in position is the same, but somebody who's traveling along the ground goes a much greater distance because they're not traveling in a straight line. So displacement is how far an object is from its starting point. We have to know where it started in order to know how much it moved out of its initial position. So we looked at our do now. Dash, in the Incredibles clip, traveled the total distance of 10 meters because he went up to the teacher's chair and then he went back to his own seat, but his displacement was 0 meters. Displacement has magnitude and direction. Magnitude is a fancy way, I just realized my pointer was right there. Magnitude is a fancy way of saying size. Direction is incredibly important. Think about getting started with a race. If you run forward and your opponent runs backwards around the track, how do you judge who comes in first? Same thing, that 7-year-old who finally hits the T-ball and runs straight to third base instead of to first base. What happens there? We use this delta x symbol for displacement. It literally means final position minus initial position. So we calculate that, and you'll see that represented like this with a little delta x equals x sub f minus x sub I. This says the change in position is equal to the final position minus the initial position. And we can measure displacement using any of the various length units, meter sticks, rulers, paces, you name it. In here we'll use meters. Okay. Velocity. I'm going to put myself back in the corner over here. Displacement in a given time interval. It includes magnitude and direction. So displacement is the change in position. So velocity is the change in position over time. It's displacement divided by time. So we write it like this with a little v for velocity. It's equal to displacement, that change in position, divided by change in time. Or sometimes you'll just see a little t. Go away, little thing. I need to see the screen. So this is technically average velocity. That's not an important distinction right now for what we're doing, but I didn't want to lie to anybody. Displacement in a given time interval includes magnitude and direction, like we just said. Our units are meters per second, m/s. Average speed is similar, but you'll notice this doesn't say displacement. Speed is distance traveled in a given time interval. So think about that first example I said of giving someone directions to travel over land to get from where you are to Northurston High School. They've got to go down the road, then they've got to cut across the trail, then they've got to pass by the hardware store, then they've got to hit the roundabout. They're going to travel a much greater distance. And even if it took the same amount of time as someone gently flying through the air to Northurston High School, that distance is an important piece of the calculation there. So sometimes you'll see a little s for speed, and we'll use a little d for distance occasionally. So we had a little discussion in the chat, and this was really helpful. Does a car speedometer measure speed, velocity, or both? Well, speed does not equal velocity. Velocity includes magnitude and direction. So the speedometer says the same number whether you're driving forward or whether you've put the car in reverse. Velocity would call one of those directions negative to show that it was opposite of the other. So maybe the forward direction is positive. So when the car is in gear and driving forward, that is positive, 15 miles per hour. And if the car is in reverse and someone is backing out of the driveway way too fast, by the way, they're going negative 15 miles per hour. So a speedometer measures only speed. It doesn't measure velocity. Think about it. That's why we call it a speed limit, right? It doesn't say a velocity limit. Otherwise, the direction would be important, right? You'd have to have a sign that says, well, you could drive only 20 miles per hour in the school zone down the street this way. But if you're going that way, no problem, 90 miles per hour. So we discussed an example of two cars that have the same speed but different velocities. People gave examples like, okay, two cars are both going 60 miles per hour, but one is driving north, one is driving south. So same speed, but different directions. That means different velocities. Someone gave the example of a car driving and a car falling. So that is actually a really exciting thing to watch. And I'll find a video clip that covers that because it's super cool. Oops, I clicked the wrong button. Last word from today, acceleration. This is the change in velocity for a specific time interval. We write it with an A for acceleration. Again, that delta, which means change, so change in velocity divided by the change in time. And the unit for acceleration is one we don't usually see, meters per second squared. That's because both velocity and acceleration are terms that require math in order to derive them. Think about it. When you see a car drive down the street, you can compare it to some other motion and say, ooh, it's going fast. But how fast? Can you see 33 miles per hour? No, you can't. You have to calculate that by measuring a displacement divided by a time. The universe consists of four things: matter, energy, space, and time. We are very good at perceiving those four things. So you can see the matter of a vehicle driving down the road. You can observe the distance, the amount of space it travels, and then you can sense the amount of time that passes. Or we've developed tools that make a more regular measurement of that passage of time. So we can't see speed. We can't see velocity. We can't see acceleration. We can only say, I notice that the distance is changing over time. And then go, oh, I notice that it's changing more and more and more because something is speeding up. You're actually doing math every time you make that observation. Your brain is doing it for you. So we've got that meters per second is our unit for velocity, divided by seconds is meters per second squared. Think about when we talk about the acceleration of a car. So Tesla, for example, can go from 0 to 60 miles per hour in 2.4 seconds. So even cars that we talk about for real, when we want to describe how quickly they can accelerate, how quickly they can speed up, we don't give a number. We give a math problem. We say, okay, change in velocity. The initial velocity is 0. The final velocity is 60 miles per hour. So we find that change, 60 minus 0 is 60 miles per hour, divided by 2.4 seconds. And we actually just say the math problem out loud to describe the acceleration of a car. So that was the basic description of, our basic summary of what we covered in class today. All right. So please, I hope that was helpful for folks. Go ahead and get started with your lab.